Now that we know about our imaginary numbers or our complex numbers, we can find solutions to all of our quadratics regardless of if they have imaginary solutions or complex solutions or if they have our real numbers solutions. So we're just going to practice a few of them. Again, when you're using the quadratic formula, you need your a, b, and c. Remember that a goes with x squared, b goes with x, and c is by itself. So before you start solving, it has to be set equal to 0. So here, this is already set equal to 0. So I can just go about doing my quadratic formula. So remember, we have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So then here we get x equals negative b, so b is negative 3, so negative 3 plus or minus the square root of b squared, so negative 3 squared, minus 4 times a, which is 9, times c, which is 9, all over 2 times a, which is 9. Right? So if we color code, those 9s belong to that 9. This negative 3 belongs there. And this 9 belongs to that. Okay. Now you don't have to color code, but just so you can see that that's where it came from, that's what the color coding can help you with. So then I'm going to simplify what's under the root. Notice when I put in my negative 3 quantity squared, I have to have parentheses. If you don't put the parentheses there, it's incorrect. You may make a double error, like 2 mistakes that undo your original mistake. But if you drop the parentheses, this is incorrect. So make sure you're putting that in parentheses. The reason it's incorrect is because negative 3 squared is different from 3 squared. This says negative 3 times negative 3. This one says, or negative 3 squared. This says 3 times 3 and then times it by a negative. So this will give you positive 9. This will give you negative 9. So that's what the difference is. That's why you put the parentheses when you're plugging in negative numbers. So I like to find what's under the root first, or remember we also refer to that as our discriminant. So negative 3 squared minus 4 times 9 times 9, which gives us negative 315. So since our discriminant is negative, that means that I'm going to have 2 imaginary solutions. So here we've got the negative 3, which just flips back to a positive 3, all over 2 times 9, which gives us 18. So remember that when we've got 315, we're really going to break that down to be the square root of negative 1 times by the square root of 315. And then I break down 315 like we normally would. I know that it's divisible by 5 since it ends in 5. And then it goes into it 5 goes into it 63 times, so I divide by 7 and get 7 and 9. Or you can do 6 plus 3 is 9 and know that 9 goes into it and then 7 times. This is 3 and 3. So we'll have a group of 3's that will come out. The 5 and the 7 have to stay underneath. Right? And then don't forget the I comes from the square root of negative 1. And then the 5 times the 7. Right? Those are our loners that have to stay underneath the root. And then we still have the 3 plus or minus over 18. So remember, when you have things underneath the root, you still have to multiply them. So then this, I'm going to come up here, turns into 3 plus or minus 3i root 57. Nope. 5 times 7 is what I wanted to say. So 5 times 7 gives us 35 all over 18. I look to see if any of these are divisible by a common factor. All of those are divisible by 3. So I'm going to divide the 3 by 3, which gives us 1, the 3 by 3, which gives us I root 35, or 1i root 35, and then 18 divided by 3 gives us 6. Now remember that this is really representing 2 answers. 1 plus I root 35 over 6, and 1 minus I root 35 over 6. So because we got the discriminant was less than 0, we know that there are 2 imaginary answers. Or complex is the other way that we look at it. Okay? So notice we got 2 of them here, which means when I go to graph this, I should expect that it's above the x-axis or below the x-axis. So here, since this is a positive a squared, it has to be opening up, so that means I'm going to be above the x-axis. Or I can look at my y-intercept and say, well, my y-intercept is positives, and it's opening up, so it has to be above. All of those are good ways to do. Okay, let's take a look at another example. If I give you 5x squared minus 12, actually, I changed my mind. Let's do negative 3p squared plus 2p plus 12 equals 2p squared minus 5p. Okay? Now this one looks longer, which it is originally, but it's still not very much more complicated. All I need to do is get everything over to the left side or everything over to the right side. Okay? Now, I typically like my p squareds or x squareds, whatever variable is squared, I like it to be positive. So if I subtract my 2p squared to this side, I'm going to end up with a negative 5p squared. So I'm going to choose to move all three of these to the right side. It's not going to matter either way you do it. You'll end up with the same answer at the end. So just be aware of that. I usually do that when I'm solving quadratics because I usually check to see if something's factorable. We're looking at the quadratic formula, so I guess it wouldn't really have mattered, but in general, that's my plan. So I'm going to subtract 2p, subtract 12. So then we get 0 equals 5p squared. Negative 5p minus 2p gives minus 7p, and then minus 12. Okay. So then we are using the quadratic formula, so this is going to be a, b, c. So then we do x equals or in this case it's p. X equals negative b, so negative 7 plus or minus the square root of b squared, so negative 7 squared, minus 4ac, so 4 times 5 times negative 12, all over 2a, so 2 times 5. Okay. So again, I'm going to find the discriminant. The discriminant's the thing that's under the root, so negative 7 squared minus 4 times 5 times negative 12. So that gives me 289. So 289 is greater than 0. So because we know that this is greater than 0, I'm going to have two real solutions. So the next thing we look at is this a perfect square? So I'm going to put the square root of 289 in my calculator and see if it's a perfect square. And in this case it is. So since we know that this is a perfect square, we know it's going to be two rational solutions as well, meaning that they can be written as a fraction. If it wasn't a perfect square, then I would have two irrational solutions. So we have negative 7 plus or minus the square root of 289, which we found to be, and which was 17, all over 10. So remember, this is really two answers, negative 7 plus 17 divided by 10, and negative 7 minus 17 divided by 10. So negative 7 plus 17 gives us 10 tenths, and negative 7 minus 17 gives us negative 24 tenths. 10 tenths is really 1. 24 tenths, negative 24 tenths we can reduce, divide each of those by 2, so that gives us negative 12 fifths. So notice here, both of these are rational, first of all, which we knew from up here. But if we get rational answers, that also means that I could factor. So it's important that you're paying attention to the instructions. If I don't specify in the instructions which way you need to solve it, I don't care which way you solve it. You could use the quadratic formula, you could use completing the square, you could use factoring. If I say in the instructions that you have to solve using completing the square, then that's the way you have to do it. If I say you have to solve it by factoring, then that's the way you have to do it. Now, just so you can see that you'll end up at the same spot, if we do our factoring here, we have 5 times negative 12 and adds to negative 7. So we're multiplying to negative 60 and adding to 7. So we've got 1 and 60, 2 and 30, 3 and 20, 4 and 15, 5 and 12, and 5 and 12 are the one that get us there. So I need the 12 to be negative, the 5 to be positive. Remember, we have to pay back our 5. We'll put it on top. Then we look for a common factor. We get 1 and 1. 5 and negative 12 have no common factors, so then I get x, oh, we're with p's, just kidding. P plus 1 times 5p minus 12. And we set each of those equal to 0, so we get negative 1, and then we set this one equal to 0. If we set this one equal to 0, we have 5p minus 12 equals 0. So we're going to add 12. So we get 5p equals 12. Then I have to divide by 5. So we get p is 12/5. So what happens is that we have this shortcut. We had the shortcut before where we changed the sign from here to here. But if we have this number in front, you change the sign from here to here still, but then I divide by this number in front. So you can still do all of this work, but you can take the shortcut that you change the sign, divide by this thing. Okay? So notice that either way we did it, we came up with the same answer. Right? So there's lots of ways to solve quadratic equations, but you can always use the quadratic formula, and you can always solve by completing the square. Sometimes you can solve with factoring, not all the time, and then sometimes you can solve with your square root property. So let's take another example. So if we look at this one where I've got negative 16x squared minus x equals negative 8 squared plus 10 minus 2x. Okay. Again, before solving a quadratic, we know this is quadratic because our highest power is 2. Before solving it has to be set equal to 0. So we had moved all of these to the right side, so let's move these to the left side. So add 8x squared minus 10 plus 2x. So add 8x squared plus 2x and then minus 10, so that gives us negative 8x squared plus 2, nope, I missed my like terms. We've got the like terms of negative x and x. It's negative x and 2x, wow, is x, and then minus 10 equals 0. Okay. Now notice our a squared is negative, which is fine. If I'm trying to factor, I would typically pull out the negative, so I would do 8x squared minus x plus 10, and then I would say, well, can I multiply to 80 and add to negative 1, which I can't, which means I can't factor it. But if you are factoring and you end up with a negative x squared, know that it's possible to just pull out a negative 1. Okay. So we have, this is a, b is the unsaid 1, c is the negative 10. So x equals negative b, so negative 1 plus or minus the square root of b squared. So, 1 squared minus 4ac, so negative 4 times negative 8 times negative 10, all over 2a, so a is negative 8. So if we look at a discriminant, remember your discriminant is the thing underneath the root. So if we do 1 squared minus 4 times 1 squared minus 4 times negative 8 times negative 10, that gives us negative 319. Okay. So since this is less than 0, that means I have 2 complex or imaginary solutions. Okay. So this is negative 1 plus or minus the square root of negative 319 over negative 16. Okay. Well, if we look at 319, if I do 3 plus 1, that's 4. 4 plus 9 gives us 13. So it's not divisible by 3 or 9. It's not even, so it's not divisible by 2, which means now we also know it's not divisible by 6. If I look at my last 2, that's not divisible by 14, so it's not divisible by 14, so I'm going to try 7 and a couple other numbers, and none of them work. So the only thing that I have to do with this is then take care of the negative. So remember that this is really the square root of negative 1 times by the square root of 319. So it's negative 1 plus or minus I root 319 over negative 16. Okay. Now there's no number to simplify other than 1 that goes into all 3 of these. However, it's unconventional for us to have a negative in the denominator. So what we usually do is we move it to the front or to the top. Okay. So we would move this so it'd be negative, and then negative 1 plus or minus I root 319 over 16, or I would take it and I would put the negative on top, which means I would have to distribute. Okay. So if I distribute the negative through, it becomes a positive 1, and then since we have plus and minus, This will turn to negative. This one will turn to positive. So we'll still end up with plus or minus I root 319 over 16. Right? So what happens is because the negative was here, it changes the sign of this one. It changes both of these signs, but since we have plus or minus, it remains plus or minus. So this sign changed. These ones technically changed, but they just are the opposite of each other. So since we have both of those, they remain the same. Okay? So just be aware of that negative possibility. Now let's try one more. So if I have negative 5n squared minus 3n plus 6 equals 3. Okay. Very first thing when you're solving a quadratic is that you have to set it equal to 0. So I need this 3 on the other side. So we're going to subtract 3. So negative 5n squared minus 3n plus 3 equals 0. Okay. So again, we locate our A, B, and C. So this is A, this is B, this is C. Remember, A goes with the squared. B goes with the 1 to the first power, and C is the constant. So then we do our formula. So in this case, it's n. X equals negative b, so negative negative 3, plus or minus the square root of b squared, so negative 3 squared, minus 4ac, so 4 times negative 5 times 3, all over 2a, so 2 times negative 5. So I'm going to simplify the negative negative 3, which is positive 3. I'm going to find my discriminant. Remember, the discriminant is the thing that's underneath the root. So again, remember to put your parentheses, negative 3 squared minus 4 times 5, sorry, negative 5 times 3, which gives us 69. Okay. Since this is greater than 0, that means that we will have 2 real solutions, right? Since the square root of 69 is not a perfect square, then that means we're going to have 2 irrational real solutions. Okay. So if we look at 69, so plus or minus the square root of 69 over negative 10, so I know 3 goes into that. So if we do 69 divided by 3, that gives us 23. Well, 23 is prime. So there's not anything that I can do to break down the 69. So I leave it like this, except for, notice again, we have our negative in the bottom. So I can really change this to, we're thinking negative, or positive divided by this negative gives us a negative, and then positive divided by negative is negative. Negative divided by positive is positive. I don't know what I was saying. Positive divided by negative is negative. Negative divided by negative is positive. That's what I wanted to say. So plus or minus root 69 over 10. Okay. So again, this is representing 2 solutions. It's irrational because we still have that root. And that's how we work with the quadratic formula, including when we have our imaginary numbers.